On Tuesday, May 6 at 7 a.m. in Silicon Valley, 10 a.m. in Washington, D.C. and 4 p.m. in Central Europe, our global photonics community comes together online to tackle one of the most critical enablers of environmental and industrial innovation: gas and liquid sensing with photonics. Gas and liquid sensing has quietly become foundational to sustainability efforts, process safety, food integrity, automotive innovation, and environmental compliance. But while the technology powered by spectroscopy, fiber optics, and mid-infrared sensing has advanced dramatically, integration into industrial and real-time systems remain a major challenge. So let's continue the discussion. We have a strong lineup of thought leaders, but this is not a webinar. This is an online gathering with the goal of establishing partnerships. Join in the room with Dave Nelson, President of Aerodyne Research, who will offer insights from one of the world's leading atmospheric monitoring labs. Arindom Saha from Tech5 USA, who will discuss translating spectroscopy into practical process analytics. Alexander Novikov, R&D lead at Art Photonics, who will highlight developments in fiber-based sensors for in-situ monitoring. Daniel Pearce, Head of Applications at Living Optics, who will introduce applications of hyperspectral imaging for liquid and gas sensing. Thomas Rasmussen from Ibsen Photonics, who will speak on rack compact spectrometer integration. Jean-Philippe Gagnon, Field Application Engineer at Telops, who will bring high-resolution infrared sensing into the picture. And Mathieu Carras, the CEO of mirSense, who will share advances in quantum cascade lasers and mid-IR sensing platforms. We are pleased also to welcome Erik Schreuder from LioniX International, who will add perspective on scalable integration and packaging. Over 90 minutes, we'll dive into 5 critical themes. Number 1, industry-specific sensing needs and unmet challenges. Number 2, innovations in tunable sources, miniaturization, and packaging. Number 3, deployment barriers in real-world environments. Number 4, pathways to commercialization and regulatory alignment. And number 5, the role of collaboration in accelerating adoption. This meeting is interactive, so please stay engaged, use the chat, and join the discussion in our Zoom room. A big thank you to Optical Systems, whose sponsorship allows us to keep these conversations free and open to the community. We are ready, let's get started. Thank you so much, Olga. Thank you very much, everyone, for joining on this spectacular afternoon on gas and liquid sensing. It is an honor for us to have NIST, to have Aerodyne, to have Tech5, to have some of the key companies in this business talking not only about what they do, but how they can work together. This is what we want to achieve on the next 1.5 hours. We want to make sure that all of you here in the Zoom room with me find potential partners, suppliers, and customers. So please, as I said in the video, use and abuse the chat. Say there what you do, who can help you, how can you help others, ask questions. You will always have the time to voice those questions. I would like to start by saying that I thank so much the sponsorship of OptiWave. Thank you very much for sponsoring and showing your brand on this very important topic for you. Thank you for bringing your simulation and design software to the table. I also would like to thank the people who are here leading the discussion, but everyone in the Zoom room with me will be participating. But Aerodyne, Tech5, Art Photonics, Living Optics, Ibsen Photonics, Telops, mirSense, and LioniX, thank you very much for being with us today. And also, I would like to highlight that this is a part of the series, and we have announced all the meetings all the way to the 10th of February. The previous meetings are in YouTube, so you can watch all of them. But in a couple of weeks, there is an exception. In a couple of weeks, on the 20th of May, the topic is defense and security. That meeting will not be in YouTube. If you want to participate at that meeting, you need to register in advance, and we will not live stream it. Everything that will happen on that meeting will happen in the Zoom room, will stay in the Zoom room, will disappear after the meeting is finished. I want to highlight, in 2 weeks, 20th of May, the meeting will not be recorded and will not be live streamed. So please feel free to secure your spot by registering as soon as possible. With that said, today is all about gas and liquid sensing. And Olga Ras is here with me to make sure that all of you use the membership benefit accordingly. So please make sure you continue supporting us by being a corporate member, getting access to the market reports or events, and of course, all the different engagement opportunities. One of those is our library of market reports. All of you have access to more than 100 market reports in the library, optica.org/market reports. Please continue being a member and please use your membership and download all the market reports that we have for you. With that said, I would like to also say hello to the YouTubers. Hello, YouTubers of the world. Thank you very much for being with us today. If you have a question, write it in the chat and I will read in the Zoom room. And this, of course, also valid for the people here with me in the Zoom room. All of you, of course, have access to all the different slides that we're going to discuss. They're going to be shared with all of you after the meeting, but please make sure that any question, any comment, any suggestion, or simply what you do in the field of gas sensing is written in the chat after the meeting. We will also share the chat with all the participants and our corporate members. Olga, we are ready, right? We have a participant list, a fantastic group full of people, companies like, I can see, let me look. I have Lithium, that you do a thin film lithium niobate. I have, of course, our friend Zainab Kordi. Thank you for all the constant support you give to us. OptiWave, thank you for supporting. Olga, what's going to happen in the next 1.5 hours?
Well, we're certainly going to have a very interesting conversation that I'm very much looking forward to. And I'm very happy to see so many industry participants, Lithium, Luminar, OptiWave. Thank you once again for being sponsors. But let's start, because today's discussion, I think, is a very fun topic, and it gets, in the last years, it gets more and more track of really being important, and not only for eco-monitoring or for ecological observations, really for industry. So let's see where it all goes. And of course, with this such a start, I would like to introduce as the first speaker to the floor an authority, an unquestionable authority in this field is National Institute of Standards and Kevin Cossel. So Kevin, please tell us what's new, or what are the trends, what are the challenges in the gas and liquid sensing, how you address it, and what remains a challenge. You're very welcome to the floor. The attention of everyone is yours.
All right. Thanks for the introduction. Yeah, so I'm Kevin Cossel from National Institute of Standards and Technology in Boulder, Colorado. And so I have a few slides on kind of what we do, so I can start sharing those.
Go ahead.
Our work is focused on in our group, at least, on atmospheric monitoring with dual comb spectroscopy. And these are just a few photos from various kind of field deployments that we do. So, we really are trying to work on taking our instruments, mostly that we develop at NIST and then with industry partners, out into the field to do measurements. And so the first thing I kind of wanted to highlight is that, atmospheric science is very complicated. So what we're trying to do is we're trying to measure sources, and we're trying to measure pollutants in the atmosphere. Some of those pollutants are produced directly by sources, and then a lot of them are also produced by reactions in the atmosphere. And we're trying to understand all of those things. And so in order to do that, we need to detect many different gases. We need to detect it at kind of part per billion level concentrations. And for many applications, we also need to detect it with high accuracy, because you want to compare measurements in one location or another, measurements with different instruments, so that everything is intercomparable. And what we do, and what a lot of the other people who'll be talking are doing, are leveraging advances in photonics to try to do this. And specifically, what we focus on is frequency combs. So many of you have probably heard of the frequency comb, but if not, just real quick, it's a pulse laser that outputs a train of ultra short pulses. And then if you Fourier transform the time domain picture, you get this comb or bunch of narrowly spaced modes in the frequency domain. So you have this broad spectrum with accurate and well-known frequencies. And what we do is we take two combs and we stabilize them so that they have slightly different pulse rates. And we use them to measure a spectrum, much like Fourier transform spectroscopy. So one pulse from one comb walks across the pulses from another comb, gives us an interferogram. We can Fourier transform that, get a spectrum, much like a Fourier transform spectrometer, but now in with kind of no moving parts. But you do have to have all these lasers be robust and stabilized. So that's one of the challenges. To do the open path measurements, what we do is we take these pair of combs and we send them out a telescope system to a reflector somewhere. Light reflects back off and we measure it back at the telescope. And then we can have that telescope point around to different reflectors as we want. And the reason we're doing this, again, is we're trying to do accurate measurements. So the frequency comb gives us a negligible instrument line shape. So it gives us the ability to accurately measure spectra, which we can then use to get accurate concentrations. Because we want to be able to measure multiple species, we need it to be broadband. And the kind of laser aspects of the frequency comb allow us to try to do these open path measurements, which allow us to get just kind of a different measurement modality that gives us spatial averaging, being less sensitive to wind to try to measure try to quantify emissions from sources as opposed to just quantifying concentrations. And some of the directions that we've gone at NIST, we are looking a lot at agricultural gas measurements. So looking at having our system deployed in feedlots to try to measure emissions of methane and other greenhouse gases and ammonia, which is a air pollutant important for sort of regional haze, and measure them at feedlots, and then be able to engage in really get these out into the field so that people can use them to start looking at mitigation options and compare emissions from two different scenarios or different feeds or different treatments in different parts of the feedlot or things like that. We've also done measurements where we've tracked a reflector on either a tethered balloon or a UAV. And so now you can start scanning this around. This one, it was a fun project. It was cool, but one of the limitations we have is, being able to track moving objects really well and also being able to have this UAV fly for long durations. We've looked at volatile organic compound emissions from oil and gas operations. So we had a system measuring from an oil and gas drilling operation on our laser beams went on kind of multiple different sides of this drilling operation. We could look at some of the VOC emissions there. And then looking at urban and regional emissions and air quality. So we've had a few different field campaigns where the instruments up on the roof of a building targeting different reflectors at different places around and looking at both greenhouse gases and VOCs related to air quality. One thing I wanted to highlight is, at NIST, we do technology development, and we do a lot of measurements to, help identify or, help with standards development and kind of our focus is technology development with looking at accuracy and traceable standards and things like this, right? As part of that, we do a lot of tech transfer. So, we do have a goal of technology that we develop at NIST can be transferred to companies. We can do that with CRADAs, we can do NDAs, we can do other transfer agreements, and we've worked with companies and universities. In fact, this comb technology has spun out into company for oil and gas monitoring called Long Path Technologies. And we've done transfer of frequency comb systems to multiple other companies as well. And so kind of just to end some of the outstanding challenges as we've seen it is, one thing I've tried to stress this throughout is like, how do we determine the precision and accuracy, both in the lab, but also in the field? And so for open path measurements, this is really challenging, but even for sort of in situ point measurements, it can be very challenging to check for interferences. How do you make sure that in all environments, you're really seeing what you want to see? And then, always a quest for improving the signal to noise ratio and detection limits. So that's new technology that comes in with this other point, and how do we detect other gases? How do we work in other wavelength regions? That would also help improve the sensitivity. How do we detect gases that have very broad absorption features? That comes back to some of the precision and accuracy challenges, but that's where you need, broad bandwidth. And then how do we make the system smaller and lower size, weight, and power? And I would say from our perspective, for a lot of field measurements, power is one of the key drivers, really. You need, because we're trying to put these out in trailers, in vans, and in sites on roofs, you need low power so that you can work off of one circuit, and you can have temperature control in whatever building you're in, or in whatever trailer or van you're in, and things like this, without having to ask for multiple different circuits from different places. And then some other questions about how do we really get the new techniques into different communities and figure out what other communities need, and how do we interpret different sets of data. So lots of different challenges in different directions. And with that, I just wanted to kind of acknowledge the group at NIST. Of course, it's not just me, right? It's a huge group of people who worked with, and a bunch of our collaborators at different universities, at health department, and some of our funding agencies.
Thank you very much, Kevin. Kevin, so you have quite a group here in the room of the really, guys that are working in photonics, provider of the photonics solutions. So if you can name, let's say, your top 3 challenges for photonics, whether it's lasers, stabilization, or I don't know, as you mentioned, signal to noise. But let's pick that maybe these 1, 2, or maximum 3 that keep you up at night. What would that be?
Signal to noise ratio is the biggest one. So, and that basically signal to noise ratio for combined with, picking which gases you want to measure. So basically being able to generate enough spectral power in our region of interest for where the gas absorbs at. Because unfortunately, you need to target the different absorption features where they are and where they're strong, and not where your laser works well at. So being able to broaden the spectral coverage of the laser systems, and maintain good power where we want it, and not have a bunch of light where we don't want it instead. That's kind of the biggest one, I would say. And then still a lot on overall robustness and power consumption. It's kind of the other directions, I would say.
Do you also see the trends, for miniaturization? Because that sometimes increases the robustness, right? If everything is assembled and well integrated, it improves the stability.
It does, yeah. So, I would say kind of up to a point where you don't lose performance is the one key thing, right? So focusing on miniaturization just for miniaturization doesn't always, is maybe not always the best option. Being able to have a compact system that you can reliably temperature stabilize, but gets back to the first point, the signal to noise ratio for the gases that you want to measure is maybe a bigger sort of
bigger
issue.
nightmare.
Yeah, exactly.
We have a couple of questions for you in the room. So one of them is from Ahmad Atif of Optiwave. Ahmad, please unmute yourself and ask your question.
Thanks, Olga. Thanks, Kevin. It's a great presentation. I have actually a few questions. I'm not sure. The first
Go
one
ahead.
is related to the tracking mechanism you mentioned about UAV. What is the kind of concept there? Any idea?
Yeah, so I mean, basically what we do is we use image processing, and we have a beacon LED, which is either on the UAV or on the ground telescope system, then reflects off of the retroreflector, and then we use an image processing algorithm to just keep the return bright spot centered on the camera, or in where you want it to be on a camera image.
Perfect. The other question is about the scintillation. I mean, does it affect your accuracy or spectroscopy measurement accuracy, or it's not relevant in this?
It definitely affects the signal to noise ratio. It doesn't affect the accuracy, and that's one of the advantages of the dual comb spectroscopy, is that we are measuring an individual spectrum faster than most of the turbulence speed. So an individual interferogram is captured basically in nominally a static atmosphere. Interferogram to interferogram, there are changes in total power. And so if you're doing tunable laser measurements, or if you're doing slower scanning measurements, you do need to be careful that you don't get distortions from scintillations kind of during the time of one scan.
Okay. I'm not sure if I can ask a more question, but
Go ahead.
okay, thanks. The last question is about like you mentioned, signal to noise ratio is an important issue for you. How about like, are you using balance detectors and some kind of schemes to improve signal to noise ratio in general?
We definitely think about that, and we have been trying to figure out how to do that. And actually, that is one of the somewhat photonics related challenges, is just getting better detectors, right? So we actually do, depending on which wavelength region, we have worked on home built designs for transimpedance amps that have low detector noise. Balance detection we haven't figured out the best ways to implement it on open path measurements yet. So we're still figuring that out.
Since we are a sponsor actually to this talk, we try to advertise our simulation tools. We can do simulation, balance detector simulation. And if you are interested, we can talk about it.
Well, actually,
Ahmad, I heard that you have...
Actually, Scott Newman is in the room. If you have already mentioned it, Scott, why wouldn't you present and share your slide?
I can certainly do that. Give me a moment to share my screen here. I want to make sure I actually share the right one. Can everybody
Yes.
see that there?
Yes.
Perfect. So OptiWave provides a broad range of advanced CAD software packages for optical system design. Our products are licensed by more than 1,000 industries, leading corporations, universities, research and government institutions, and we have pretty worldwide customer base in 80 different countries. We provide packages that look at the component level, so individual components. We have instrument level for instrument control and communication, and then we have our system level products. Dr. Atier is the product lead of the OptiSystem product, which is our lead kind of flagship product in that regard. The component level products include finite difference time domain, beam propagation, mode solvers, and they typically target structures that aren't very well defined analytically. You want to be able to discretize the structure. So we do a lot of work with multi-core fibers, photonic crystals, photonic crystal fibers, stuff like that. So the example here was a temperature sensor that we pulled from a paper and we reproduced it, demonstrating the temperature monitoring capabilities of this multi-core fiber. At the instrument level, OptiInstrument has the ability of interfacing with different products, physical products, measurements, sources, detectors. And basically what it allows you to do is automate either your test bench or your QA bench. The example here we have is a measurement system set up for the free space optics collaboration that we are undertaking with the University of Ottawa. And then at the system level, OptiSystem is a very broad range product. They have hundreds, if not thousands, of components at this point, capable of modeling anything within an optical system that you want to model as a whole, from source all the way down to detector. They basically are providing the ability of modeling those full systems. And the highlight for this particular group, I think, besides the free space optics functionality that Dr. Attier has already touched on, is our ability to integrate both within our own products as well as external products. So the example that we demonstrated in one of our application notes that I pulled out for this particular group is this particular paper here where they have a trench-assisted multi-core fiber. And what happened was we were able to model it within the OptiMode, so one of our component level products, so a structure that isn't very well analytically characterized. We characterized it in OptiMode, pulled out that characterization, and that could then be included within OptiSystem as this optical fiber. So, for example, companies like Corning or others that are doing exotic fibers or non-traditional fibers are able to actually pull those fibers into a full system level model. But we have integrations also with Siemens. We have PDK integrations with Lucida. So we're putting a lot of focus on integration at this point.
Thank you very much, Scott. We actually have a company which does fibers in the room, so I'll bring them back later. Maybe it's an interesting connection. Meanwhile, yeah, tell me.
Sorry, I was just going to comment for that fiber group, if we don't connect, the OptiMode product actually has the ability to import refractive index distributions. So you can actually do the measurements of your fiber, pull it in, and do the mode analysis on it.
That is very useful. Thank you. Meanwhile, we actually have another question from Qualivian. Sandeep, could you please unmute yourself and ask the question?
Yeah, hi Kevin. So my question is related to, are you developing any kind of on-chip nonlinear optics to generate these dual-com frequencies?
Yes. So I was so we in particular we've tried to do some work on spectral broadening of our erbium-based frequency comb sources with nonlinear optics on chip. You know, it's promising, but so far one of the major challenges that we've had is that we just see in the spectral broadening process, we see extra loss. So, you know, if we try to broaden, you know, one of the wavelength regions we want to be able to hit more reliably is kind of the 2 to 2.5 micron spectral region. And if we try to use on chip nonlinear optics to do that, we see a lot of nonlinear loss that ends up, you know, producing light somewhere else that we don't entirely know where it goes, but we only get a milliwatt or two of light at this off chip at kind of the 2 to 2.5 micron spectral region, even though we're putting in 100 milliwatts with high coupling efficiency. So those are the sorts of challenges we've still run into with the nonlinear optics on chip.
Understand. But how does the light is being sent out to the space and collects back to the chip?
So we don't couple back into the chip. We will couple off the chip into fiber and then either do the detection just off of a beam splitter in free space or with, you know, circulators or things like that in fiber afterwards. And I guess the one thing I would say for the on-chip frequency combs is that the repetition rate of those are always a lot higher. And so that's one of the reasons we haven't done a whole lot looking at that, because the repetition rate sets your spectral sample spacing, your mode spacing. And for, you know, a lot of lines in the atmosphere at, you know, atmospheric pressures are, if they're well-resolved lines, they're, you know, 5 to 10 gigahertz wide, in which case, you know, you really want kind of gigahertz repetition rates or maybe below, which are hard to get on chip from on chip frequency combs. Those are more 10, 20 type gigahertz.
Thank you. Actually, because one of your wish list points was also, a different wavelength or different wavelength region. Can you maybe say a couple words about this? Which wavelength
Yeah.
regions you're
Yeah.
interested?
So, I mentioned the 2 to 2.5 micron spectral region, mid to longer wave infrared, so 3 to 5 microns and 8 to 12 microns.
That's a
A
very
little,
long list.
yeah, basically those. A little bit kind of in the more
mid-IR
in the
range.
in the mid-IR and a little bit in the visible, but mostly
So,
mid-IR long wave.
That's in this respect, I would like to invite to a conversation Mathieu Carras from the mirSense, who is exactly specializing in the quantum cascade lasers in the mid-IR. Mathieu, tell us a little bit more about what you do and what you can offer for the wish list of Kevin.
So mirSense is specialized in mid-infrared quantum cascade lasers, and in terms of wavelength coverage, just mentioning that we are able to go from 3 micron up to 20 microns. So I just mentioned that because the usual wavelengths for quantum cascade lasers usually stops at 10 to 12, but we do have a technology that we develop in Montpellier here that enable to go up to 20 micron. So for some specific species, that's very interesting because, for instance, you can reach benzene detection of BTEX like benzene, toluene, xylene around 14, 15 micron. And you can also have some OH bound at 19 micron. So it's worth mentioning that, this can be covered with quantum cascade lasers and not with cryogenic technology, because all these lasers up to 20 micron, they work room temperature. And the purpose of mirSense is to go beyond the lasers itself and provide sensing technology. So basically, we integrate our own lasers together with MEMS microphone technology to provide compact gas sensors. And so we do target these molecules. And in order for us to be able to make miniaturization of the sensors, we use photoacoustics. And just mentioning, this is the type of footprint of product that we're going to be available next year, for instance. And this is very compact, so it's kind of a breakthrough in laser-based sensors. And this type of sensors, they only consume something like 1 watt, and they can go in the low ppb detection range for this type of molecule I'm mentioning here. So yeah, that's so we are vertically integrated, and we are able to do custom solutions, but also we provide lasers for any type of volume application, from 1 laser to thousands of lasers, and even tens of hundreds of thousands of lasers if necessary. We are proprietary of the technology, and we are as well have this IP to go to the compact sensors modules.
Thank you. Have you already passed, have you integrated your lasers or your lasers already into existing systems? Maybe you can share a couple of words.
Yeah, I mean, we have already supplied lasers for labs, for systems, very different type of lasers. We also do lasers for defense application, for very different applications. So they are military qualified. So we are at industrial standards. And also we've been developing quite a lot of electronics. So sometimes the problem is not only the component like the laser, but it's all that's around the laser to be able to make a sensor. And so we've been developing also electronic solutions to be able to drive the QCL. Especially one problem that people have usually with QCL is that it consumes a lot of power. And when you want to do a sensor, you don't want to spend a lot of power. And so we have IPs and electronics to be able to drive the laser in pulsed operation, but with very narrow line and also very stable operation to be able to build swap sensors. Because this type of sensor, for instance, you can only afford it if you have a very low consumption electronics.
Mm-hmm. Thank you, Mathieu. Well, if there are no further questions, then I would like to invite to the floor the next speaker, David Nelson from Aerodyne Research. I think David is writing down something about the presentation of Mathieu, so it will be excellent opportunity to connect later. But please, David, you're the next. Tell us more about what you work and how you what you can offer and develop for gas and liquid sensing. You just tell her. You just tell when you want to move to the next slide, okay?
Absolutely. This is great. Yeah, so Aerodyne Research is a small business located outside of Boston. And we specialize in trace gas and particle detection in the atmosphere. Focus of this talk, of course, is on the laser trace gas and isotope monitors that we've developed. Next slide. The detection approach that we use is tunable infrared laser differential absorption spectroscopy. We call it TILDIS. And it's basically using mid-infrared lasers in a very special optical multipass cell called an astigmatic Harriet cell that gives us a really long optical path length in a small volume. Most of our work focuses in the mid-infrared region of the spectral region, and that is why I was taking notes about the previous presentation, because we do care very much about those mid-infrared sources. So we work there because that's the fundamental vibrational transitions for most molecules, and we can get extremely precise measurements by doing that. And that's really our focus, is trying to make the best possible, most sensitive measurements of many different molecules for atmospheric chemistry, for ecology, and even for geochemistry. Next slide. And so this is just a quick image showing this magical astigmatic Harriet cell that was invented at Aerodyne. And it works by having mirrors that are not spherical mirrors, but are astigmatic, so different radii of curvature in each axis. And that causes the beam spots on the mirror to execute something like a Lissajous pattern, and it fills in the entire mirror rather than making a ring around the edge of the mirror. So this promotes the spot pattern density, gives us a long optical path length in a small volume. Also, the optical quality can be maintained so that you don't have a lot of off-axis aberrations. So you get good beam quality, which reduces optical interference noise. Next slide. So we take these TILDIS instruments and we use them in a variety of different applications in the real world. And one is looking at industrial emissions. So when you drive past an industrial facility, you might have a sensor in your vehicle and you detect an enhancement in concentration. But that doesn't directly tell you what the flux of the molecule coming out of the facility is. And in many cases, what we really want to know is that flux, and we want to quantify it. So a method that we've used is called tracer release, where we'll go to the facility, and in this case, perhaps it's leaking methane, but we don't know where and we don't know how much. So we put a nitrous oxide cylinder on the facility with a known release rate, and then we drive by the facility and find the plume. And when we transect the plume, both the methane and the nitrous oxide concentration go up and down. And if you're far enough downwind, they go up and down together because they're fully turbulently mixed. And in that case, that means that the ratio of the downwind concentrations is also the ratio of the fluxes at the source. So by using this method, we can do quantifications of total leaks coming out of industrial facilities with accuracy of 10% or even better, depending somewhat on the wind conditions. So we've done this with natural gas for years. Recently, we've been extending it to hydrogen because of the build out of the hydrogen economy. So the next slide shows something there. So I'm going to skip over this just in the interest of time. This explains how our new hydrogen monitor works. But let's just assume it works and skip to the next slide. And so what you see here is measurements that we made at a test facility in Colorado called METEC. This facility is designed to test methane detection systems. It can release large quantities or small quantities of methane to the atmosphere. And what we did in this particular case is released 4 different gases simultaneously at this facility: nitrous oxide, ethane, methane, and hydrogen. and we drove around with our mobile laboratory with optical sensors for each of these molecules. And what you're seeing there is the vehicle driving through the plume. And so as we drive through the plume, you see these beautifully correlated, all four molecules rise and fall together at the same time with the same shape, because they've been turbulently mixed in exactly the same way. And so you might not know what the hydrogen leak rate is, but if you're purposely releasing methane or nitrous oxide as your tracer, then you can plot the concentration of hydrogen versus the other, which is shown on the right, and the slope of that line gives you the flux. And so we're using this now to quantitatively measure hydrogen leak rates in Europe and in the United States in various projects we're doing with the Environmental Defense Fund. It's a whole nother story, which I won't go into, but it turns out that at first you would think hydrogen is not a greenhouse gas, but it turns out that it is a moderately strong indirect greenhouse gas, and it's really important that we don't leak a significant amount of hydrogen to the atmosphere as we build out the hydrogen economy. Another direction that we're going in, next slide, is, I'm sorry, I had one more slide on hydrogen. And so this is showing, please do move forward, just my words were wrong, the slide is right. I forgot that I had this slide, which shows not a test measurement of hydrogen, but an actual measurement of hydrogen at a production facility. I can't tell you where this is or what the name of the company is because of agreements that we signed with them. But they did let us access their facility, and we did find hydrogen emissions there, and we did quantify them. Okay, so next slide. Another direction we're going in is looking at other, more molecules, so new molecules. So hydrogen is a new molecule for us. The sensor was invented in the last 2 years, but another thing we've done in the last couple of years is looked into detecting ethylene oxide. So ethylene oxide is a carcinogen. It's an extremely strong carcinogen. People are concerned with elevations in the tens of parts per trillion. And so we've developed an instrument to measure ethylene oxide with that sort of sensitivity. Again, this is one of these amazing optical cells that gives us almost a half a kilometer of path length in a cell that can fit into a tabletop instrument. And you can see on the right that the spectroscopy is very complicated. There's lots of different molecules that absorb in the same spectral region as ethylene oxide, but we've developed analysis software that can disentangle that. And so you're seeing a spectrum there that shows ethylene oxide at 22 parts per trillion. And the spectrum is super clearly visible.
Yeah, for sure, you're right. Historic pricing strategy has.
So next slide. One of the first things we did with our ethylene oxide monitors, we started sampling our rooftop. And you can see the bottom left corner, there's a green trace, and that's just ethylene oxide being blown to our building from wherever it comes. And we watched this for days and days and saw next to nothing. But then on March 27th, we saw a rather large plume, almost a half a part per billion of ethylene oxide for about an hour or so. We did high split trajectories on where the wind was coming from that day and found that, lo and behold, it did go to a facility that uses ethylene oxide to disinfect medical supplies. So we drove to that facility, that's in the bottom right. And as we drove around the facility, we saw very highly elevated levels of ethylene oxide in the tens of parts per billion. So this was a fun detective story, tracking down this molecule that is a really strong carcinogen. And there's a lot of interest in detecting it and trying to mitigate it. Next slide. Another area that we work in is soils. And so we use optical techniques, but we have to get the gas out of the soil. So we have these sophisticated soil gas probes where we can grab a slug of air that's been equilibrated with soil, put it into our instruments, and we can measure hydrogen in the soil gases. We can measure isotopes of CO2. We can measure isotopes of nitrogen compounds. This is a really productive way of understanding what the microbes are actually doing underground to understand better soil health and also atmospheric emissions from soils. And then the last thing I'll talk about, the final slide, is an extension of this where we are looking at liquids. And so we're using microdialysis probes to bring in clean water, equilibrate it with soil water. The solutes from the soil water go into the clean water, and then we bring that water back to our laser spectrometer, vaporize the water to get the gas phase, to get the solute molecules into the gas phase, and then detect them sensitively. And so doing that, we can detect nitrite and nitrate and various other molecules, and we're actively trying to expand that technology. So in summary, we're doing a lot to expand the technique in terms of looking at different molecules that haven't been looked at before. And we're also using sophisticated sampling techniques to look at gases and liquids and actually even solids in geochemistry, where we're looking at carbonate compounds and doing very careful isotopic analysis on it. But in general, our emphasis is making highly, highly precise, highly sensitive measurements. So that's all I have.
Thank you very much for this. This is great to have you here today. And most important, following what Olga said before, what are the challenges that you have for people in the room? Just give us 1 or 2 challenges we can help you with.
Yeah, so the lasers continue to be a challenge. I didn't talk about this much, but we're using quantum cascade lasers and interband cascade lasers.
Okay, can you give us a wavelength range? So let's have a nice discussion here. Give me the wavelength range that you like very much.
So 3 to 10 microns is where we are working mostly, but we would like to go beyond 10 microns. So the mirSense discussion of going out to 17 microns, that is definitely appealing to us. That would allow us to access other molecules with great sensitivity.
I think there are people in the room. First of all, Mathieu has the best QC and lasers at longer wavelengths like that one, so please work with him. There are many people in the room that can help you. Let's start by people who can measure methane. I think I asked in the chat, many of you told me that they can measure methane, so let's go first to the fiber that we're going to incorporate in Aerodyne systems. Art Photonics, Alexander Novikov, you brought here fiber that can transmit mid-infrared technology, infrared light. Can you tell us what you brought and how you could maybe convince David to incorporate your fiber?
Thanks a lot. So yeah, I have prepared the slide and let me share the screen. Just 1 moment.
It is great to have Slava Artyuschenko, a very dear person to Optica here in the room. Thank you, Slava, for being here.
Great, great. So hello, everyone. Again, my name is Alexander Novikov, and I am an R&D manager at Photonics, fiber optic company from Berlin, Germany. And we make various fiber optic devices for spectroscopy and laser applications from UV to mid-infrared up to 17 microns wavelength range. And today I want to introduce a transformative approach to chemical process monitoring using advanced fiber optic probes produced by us, a technology that enabling real-time, inline, and remote process spectroscopy. So traditional methods of chemical analysis often require sample preparation, time-consuming, and may even put technicians at risk when dealing with aggressive or toxic media, not to mention the delays in getting actual data. And that's where fiber optic probes step in to improve process analytics. So these probes allow in situ and inline monitoring of gas and liquid reactions across a broad spectral range from UV to infrared. This means that we can now observe processes as they happen in real time without interruption, without interrupting production or waiting for offline lab results. So the benefits of this approach are no needs for sample preparation, faster results, fewer human resources required, and crucially remote sensing capability, which means we can now monitor processes under extreme conditions, whether it's high pressure, high temperature, or highly corrosive environments. So depending on the application, we can use a wide variety of spectroscopic methods implemented in fiber optic probes. For liquids, it's usually ATR, attenuated total reflectance. For infrared or UV ultraviolet regions, transfection or transmission probes in near-infrared or UV ranges, diffuse reflection probes in near-infrared range used for scattering media such as milk, for example, and fluorescence and Raman probes. For gases, we also have mid-infrared transfection probes with an increased optical path and our unique infrared fibers inside that transmit up to 17 microns. And fiber probes with lab design are cost-effective, while industrial-grade fiber probes are dedicated to being used in harsh environment, high pressure, high temperature, corrosive media. We can do that. Moreover, several techniques can be combined together to improve sensitivity and accuracy of the system while being implemented into one compact combi probe. For example, you want to measure near-infrared, Raman together, we can do that. Near-infrared, transfection mode, Raman, and mid-infrared ATR, we also have a probe for that. So these fiber probes can be coupled with a variety of analytical instruments, FTIR spectrometer, NLIR slit spectrometers, or quantum cascade lasers, QCLs, LEDs, and various detectors like MCTs and others. So it offers.
Fantastic job, Alexander. And we need to ask David now. We need to ask him, David. 3 to 17 microns is a really interesting wavelength range according to what you said. I ask you first. So why are these fibers not yet in Aerodyne systems? How do you consider the use of chalcogenide fibers?
Yeah, we've considered it. One concern is that a lot of our applications, we need to couple into the optical cell and then back out of it to a detector. And so the multiple coupling steps, if you could if we could get the sensitivity we needed directly detecting within the fiber, it makes a ton of sense for us. But with the coupling in and out of our multipass cell, it's not so clear. But it is definitely something that, I mean, obviously it adds a level of robustness if you can do that.
Can I, because we'll address this issue, I think we're going to send you some information about this. We'll work heavily on this. But first, David, I would like to ask you a question. Slava, unmute the microphone. And when he does that, I stop talking. Slava.
Yeah, very shortly, David. It's a good comment, but I should say we have an experience, something like more than 30 years ago, when we coupled even not a QCL, we coupled tunable diode lasers, based on lead sulfide, and we made a coupling of fibers. So it was 4 channels. All fibers were coupled with MCT, liquid nitrogen cooled, and tunable diode laser spectrometers, because 30 years ago QCL was not available. But we couple it with 30 centimeter multipass gas cell, which was equivalent to 60 meters. So that's why you are right. There are, of course, some kind of troubles because of high numerical aperture of the fibers. But question, if customer is looking for PPT sensitivity or something like, exhaust pipe, from the car, and you really could not put QCL at the exhaust pipe. You can really put very robust fiber optic probe in any kind of, aggressive media to control in line what's going on, which is absolutely impossible when it's really bench top stuff, when you should bring gas into the system.
Yeah, totally agree with that. Actually, is anybody making pigtailed mid-infrared lasers?
We did for several projects, but it was research projects. I could not say. We did it with nanoplus lasers.
Okay.
So, project was European, 7 QCL in the range from 5 to 15 microns. It was medical purposes, and we put the bundle, it was very good coupling efficiency with tiny fibers, like 300 microns. And we put all 7 in one fiber to be used in special catheter, which goes into the knee for osteoarthritis diagnostics. So that's why, in general, with all this kind of pro and contra, I think we always should look for application, and from application we can find a solution.
Yeah, maybe I can comment on that as well. We have been working on fibering QCLs, and of course, the question is usually fibering QCL adds some cost, so it has to be worthwhile. But we've been reaching for some application where coupling efficiency is necessary. Efficiency is up to 80% in single mode fiber coupling. But then the question is, do we have such single mode fibers? So that's, I'm not sure for us, for doing, we are talking about single modes. So also the question is what type of fiber you are interested in at the end.
Yeah, good transmission without a lot of optical interference fringes being created is the goals to, well, for some applications, if you want high sensitivity, you want the optical quality to stay really clean while you do that.
We have a lot of things to discuss still, and 1 hour has gone down the drain, but so far we're having a great discussion. David, thank you very much for bringing the topic of methane sensing to the table.
Jose, can I do one suggestion? Maybe we can simply put to everybody email addresses of participants, and we can really discuss many subjects after the telecon.
Thank you, Slava. After the meeting, you all will receive the participant list with LinkedIn addresses. We cannot share emails because I want to keep my job. GDPR regulations are there. But I would like to ask David now. David, you brought the topic of methane sensing to the table. This is a bit of a geopolitical question. What is the current situation of the market in the United States on methane sensing?
Well, everything changes every day for the last 100 days, so it's hard to say. I mean, in general, environmental monitoring is not valued as much as it was 100 days ago.
But oil and gas is, and leakage is. Oil and gas is valued, and leakage in the oil pipes is valued.
I suppose, although that has never really seemed to motivate industry. They, in many cases, I think just burning off the methane or just leaking it is the most economically useful thing in remote areas. If you don't care about climate change, I think a lot of gas will be leaked.
Let's get somebody else to weigh in on that. I have in the room Jean-Philippe Gagnon from Telops. Jean-Philippe, you don't only measure methane, you see it with your cameras. Could you tell us a bit of what you do and also answer and follow up on the question I just asked David about the current situation of methane sensing?
Yeah. Hi, everybody. It's up. You can see it, I guess.
Yes.
Yeah, indeed. So yeah, all that discussion about lasers is really interesting, but unfortunately, we don't use lasers in our cameras. Oh, well, that's a false claim. We use it internally to measure to measure our internal parameters of the camera, but we don't use it to measure methane. So yeah, at Telops, we are manufacturers of infrared cameras, and more specifically hyperspectral systems, both single pixels, multi-pixels, and a fully imager hyperspectral systems. So they all use Fourier transform spectroscopy. So these are fully passive. As I said, we're not using any laser to sense the scene and measure the reflection. We're just measuring photons that are emitted from the scene, infrared photons. We do this with both ground-based systems and airborne platforms. In the recent years, I mean, we've been around since 2000 doing this type of thing, but in the last couple of years, we decided to take a miniaturization path. So all of our legacy units have been discontinued. Legacy, those are cameras that we've been making since 2005. We've adapted them and made them much more, much smaller swap. I mean. So we're based out of Quebec City in Canada, and those are cameras that we make on the lower side, on the left-hand side of the presentation. So recently, Telops, a Canadian company, is now part of a larger conglomerate of companies, let's call it this way, called Exosense. And so we're fortunate enough to, being part of a larger family, we have newer instruments to play with. But they're still based on Michelson interferometer technology. So the way we sample the gas is we have this camera, so we're looking through the gas, and if we have an imager system, we make an image at different wave numbers or wavelengths of the infrared light. So these cameras allow us to, like you said, image gas, gas that is invisible in the visible part of the spectrum. So we do some of the analysis and the research ourselves, but most of the research have been done by our clients using the equipment. And so these cameras can not only detect methane, like we spoke about, but any gas that has an absorption feature in the thermal infrared band. So we have both mid-wave and long-wave cameras. So if there's a gas that absorbs infrared energy in that spectral range, we'll see it. So I've put down here a few examples in the environment sector. The top here, the little red plume that you see is methane bubbling up from a lake. And that was imaged by a researcher at the Linköping University. They're using this equipment to mostly measure methane and other gases that come from environmental or decomposition processes, like the biofertilizer plant. So they're capable of measuring minute amount of methane with this way of measuring. So the gases that you see there are a couple ppms above normal or ambient methane levels. In agriculture as well. So the funny picture, the red plume on the right-hand side is methane being measured from a barn containing several cows, and they were able to image the methane coming out of this vent port and trace that back to the number of cows that were inside of the barn. So really interesting science. A bit funny on one side, science there. But on the more serious side, so we're using these cameras as well to measure industrial gas emissions from smokestacks and flares. In the oil and gas sectors with our methane service, we rent our hyperspectral airborne HyperCam Mini for detecting methane over oil and gas facilities in North America. So this is a complete service that we offer now. But like I said, the camera can not only detect methane but other gas.
Philippe, I've seen your
Yeah.
demonstrator myself. I think what you do is pretty exciting. And I think I encourage everyone whenever they see you in an exhibition for you to see what kind of things we can measure. I know you have a couple of more things to say on the methods, but could you address the question I asked David? Because I know you have put your cameras already in UAVs and you have measured methane and other gases as well. Let me just clarify that. What is the current situation of the market?
Oh, you mean for methane, you mean?
Yes.
Specifically? Yeah, so methane, well, in North America, especially in the US, they are the most advanced with regulation-wise. Canada is following through. We have strong commitments to lower methane emissions, both in Canada and the US, and we're in Canada, at least we're making good on our promises, I think. But the regulation is still, it's still ramping up, especially with concerning the use of those kinds of novel technologies. I mean, in North America, there's strict regulations on the way methane is measured, and now in the US with the EPA's proposal to include newer technologies like this. So we've submitted our documents and our proposal to respect the newest EPA guidelines for novel research, novel instruments. So hopefully this will go through in the next couple of weeks, months, And this is a good path, and in Canada as well. So we've been working closely with the regulators here in Canada, Alberta Energy Regulator, and other programs to get the technology recognized to make those kinds of measurements, and convince the regulatory bodies that they can use this technology securely, safely, and with good
Jean-Philippe,
precision.
I think when it comes to regulations and measurement standards, we have NIST in the room. So we need to ask Kevin, what is the current situation on methane standardization measurements?
Well, one thing to point out is that NIST is non-regulatory. So, so the regulations part, not us. But in terms of in terms of where regulations are going, a lot of it is still at state levels being developed, right? So I mean, Colorado is developing new rules for methane emissions from other sources. So I think one of the directions is that it's going to more than just the oil and gas operations. It's expanding now to look at landfills and things like that.
You have a question, Kevin, for Jean-Philippe. Could you voice your question? The question is how. No, sorry. You have a question from Art Photonics and mirSense. I will give you the floor for that question in a second. Jean-Philippe, would you finish your presentation?
Yeah, absolutely. Yeah. I can just say a few words about the challenges and so whenever we measure a gas, there's several pathways that we can follow for analysis, and we've identified two here. So in some configurations, like flares, for example, or for very low concentration gas, we have to, the processing involved the post-processing involved is quite demanding. And in these cases, we have to solve the complete radiative transfer model. So this is computationally intense calculations, but it leads to very good results. And the second way we can go about doing the processing is taking shortcuts. So by making intelligent hypotheses and assumptions about the physical model, we can simplify things and make the processing faster, more efficient, and make it real time as well. And this is what we use in our methane service. So the results that are coming in directly from the aircraft, you see the gas being detected and quantified directly from the aircraft. But for more involved applications, we have to go through the full radiative transfer, which takes some more time. And this leads to challenges for this kind of work. I'm sure you guys know or aware that retrieving or quantifying the gas emissions, not only you have to see the gas, but you have to somehow determine its velocity, the gas displacement velocity, and to be able to transfer gas concentration to leak rates measurements. And so we do this, but there's still some challenges associated with that. We're working on that as we speak. So normally we use the wind velocity as a proxy for gas displacement velocity, which in most cases works fine, but in some cases it's a limiting factor. So we're trying to see if the imagery itself could reveal, can make things better, or would enable us to get a better or a more accurate wind velocity. But also it leads to quantification accuracy. So this is a big topic here, of course. As the regulation is increasing in the US or in Canada as well, the number that we say that we've measured in leak rates in grams per second has to be pretty accurate now. And so we're working on that to make our quantification even better.
Congratulations, Jean-Philippe, on everything that you are achieving. Your cameras as part of ExoSense is a huge addition to that imperium that is being formed. Jean-Philippe, there are many people who are going to be wanting to ask you questions privately, so we're going to make lots of introductions. Yep. But let me now tell Kevin that there is a couple of people who are doing quantum sensing. I know NIST is very engaged with the quantum technologies world. One of the companies is QLM. Andrew Weld, how do you measure methane?
Hi, so at QLM, we actually have a quantum-based system, which means that we're actually counting single photons. So we have a LiDAR-based architecture. So we're imaging, and at the same time, we're combining this with absorption spectroscopy. So we're rapidly tuning our laser wavelength across an absorption line for methane at 1650 nanometers. And then we use single photon detection. So we're able to achieve that sensitivity of quantifying methane detection at up to 200 meters standoff observation. So that's how we're achieving better sensitivity by using photon counting, really. So,
Andrew, there's going to be many people who want to be part of you, and I think you already told us that we want to be part of Optica. Thank you for joining the family. Dan Pearce from Living Optics. How do you measure methane?
Hi there. Well, we're at the other end of the spectrum, so not so much methane measurements for us. We are largely in the Vis-Near region.
You have one slide for us. It's the first time that you present at the Optica industry meeting, so show your slide, speak loud about Living Optics today.
So Living Optics, we're at the other end of the spectrum. We're at the Vis-Near end, and we're an Oxford University spin-out. What I'll cover quickly is kind of our view of spectral imaging and what we're doing to hopefully change the world a little bit, one step at a time. And for us, that is about making higher volume production, cheaper systems, things that are available to a global marketplace. And so what we're doing towards that is we're bringing in a snapshot spectral imaging system, and hopefully you can see at the top, we're going to kind of walk through this single slide view of what we're up to. At the top of the screen there, you can see the difference between point scanning, line scanning, and snapshot. You don't get something for nothing. So as you move through those different modes where you're trying to get that whole hypercube in one snap, one instant shot of the world, you lose something, right? So either you have to trade off your spatial resolution or your spectral resolution or your temporal component. But for a lot of the gas and liquid monitoring, the temporal axis is really critical, right? So to be able to see what's happening live is what we're all about. You can see the top right of that slide, the encoding system that we're using. So we have a coded aperture snapshot system. And so what that means is we've got a prism in there to do the dispersion, you can see, and a coded aperture mask sat in the middle there. And we've paired that with a high resolution standard video camera. And so the combination of those two gives you the spectral data and it gives you the RGB data. By doing that, we're trying to make something that's a bit more compatible with the rest of the world in terms of the ecosystem, not just spectroscopists, not people like us that are sat on this call, but a whole bunch of computer vision people out there that really want to be able to pick up a camera and use it just as you would a normal video camera. And we've spliced in some extra bits in there. Hopefully this slide's going to move. Okay, so next thing to talk about then is why are we doing this? Why are we making that snapshot system in the first place? Well, really it's about targeting some applications where people want to take the lab and move out into the field. And so you can see this is me using it with a mobile phone attached there, looking at the health of some strawberry leaves or something quite simple there. But it gives you the concept here that we are moving away from these precision laboratory instruments and into something which is a lot more user-friendly. And that user-friendly feel is really what we're going for. So we've got a couple of videos. And that will give you an idea of what a kind of snapshot system is. Hopefully you can make out this video at the bottom left is now playing. We can see some spectra of oil and water. So we've dyed the water yellow to make it look as similar as we can to our extra virgin olive oil, and we've poured in some olive oil into there. And you can see that happening live. You can also see on the right-hand side where we've kind of classified some of those pixels based on the spectral information. So a lot like what we were talking about with Telops earlier, the idea that you can image and do spectroscopy at the same time is critical here. And that's really important for doing some of these real world applications. But it's also important for people that are just learning, that are just trying to understand how some of these systems work and to be able to experiment quickly and easily. And that's what we found with a lot of the engagements and customers we have at the moment. what they need is a system that is able to give them that data in real time, and that live feedback is pretty critical to that early adopter. And so the example we've got now showing is a classification of different liquids as we pour them from one to the other. So I'm going to kind of wrap up there quite quickly, but what you can see is the system that we have available today, which is our Visneer system. It's available as a dev kit. So if anyone wants to have a play, feel free, go on the website, you can buy one today. But if you just want to get more of a feel for what the system can do, we have a cloud portal as well. So come and say hello. There's loads of tech details on there about that. And there you go. That's us.
Thank you very much, Dan. I have a question. Why there is a little prism there? I mean, it's clear that you want to create the special separation, but why not? Why specifically prism?
So the prism choice was around maintaining that optical chain in a relatively simple form. So we could have gone for a grating or something else. But to do with the way the coded aperture system works, we're trying to minimize the overlap from the second order effects that you get from some of those systems. It also makes for something that's relatively cost effective from a manufacturing standpoint. So it's about getting the bill of materials down to a point where it's available for everyone outside of North America and Europe.
What liquids are you able now to look at? Because I see that there is a little bit of the olive oil, there are a little bit.
Sure, yeah. So we've got a few there. So we've got, there's a whiskey, there's some avocado oil. Someone's even mixed in some honey with some water for one of those as well. So these are kind of some of the fun demos that we put out there for people. But in terms of more kind of commercial use cases, we did a lot of work with kind of blood inspection and detection of trace materials.
Or food, right? Also, like because next month we're gonna have really an in-person industry meeting in the United States on the agriculture and agri-photonics. So all the photonics solution for agriculture. I think yours is definitely one of these solutions that is relevant for the meeting.
Grand. Nice to know. Thank you, and thank you for having us along today as well. It's a pleasure to be here.
And I actually want, because I got interested about this prism, and you mentioned that you can actually work with gratings, and I would like to give a floor to invite to this conversation actually a great specialist in gratings, that is Ibsen Photonics.
Yeah, so I'm Thomas Rasmussen, and I'm working with product management here at Ibsen Photonics. So if you don't know Ibsen, we are a Danish company, and we've been making gratings and spectrometers for many decades now. And actually, we are mostly 100% focused on OEM supply, which means that we supply our gratings to industrial customers and our spectrometers as well. And then they typically integrate them into larger systems for methane testing or whatever things. So we serve many different applications, but of course, we have customers that also work in the gas and liquid sensing. For example, some of the examples we have, if we build very compact spectrometers for both the near infrared and for UV measurements of various gases using absorption spectroscopy. And we've also quite a strong product portfolio for Raman spectroscopy because that's used also in some of these applications. So, and as you talked about, Olga, all our spectrometers use our in-house manufactured fused silica transmission gratings, which is kind of unique. We believe them to be the world's best and highest efficiency and most broadband diffraction gratings. So what you see here is on the graph is an example of a Raman grating, 785 nanometer Raman grating, which clearly outperforms two other technologies. So volume phase gratings, which is also a kind of transmission grating, and reflection gratings. And with our technology, we're actually able to cover basically anything from 175 up to 2.5 microns. And these high efficiency gratings, they enable several things. But one of them is, as you mentioned, to build really compact systems. If you can high dispersion gratings, you can really compress the size of the components or the modules. And also one of the nice things about transmission gratings is that even though that you have a very high dispersion and very steep angles coming off the grating, you can still get very high efficiency, like in the 90, 80, 90, up to 100% efficiency. Some of the modules we make ourselves are very compact. So we have spectrometers that weighs only 25 grams, so very small and the size of a small Lego brick. And we have spectrometers more common, you can say, up to around 4 kilos, which is more like a shoebox size. Also, one of the things that we work a lot on is the stability and the ruggedness. So we supply a lot of spectrometers to industrial applications. So obviously we pay a lot of attention to unit variation, because if you buy a lot of spectrometers, you want them to be as identical as possible, because your whole model is built around a certain spectrometer response. And yeah, so normally we work very closely with our customers to try to solve the exact problem they have. So of course we have standard products, but I have to say most of our customers buy some kind of a customized solution where we've tweaked the performance.
Perfect. I've actually...
Yeah.
Go ahead. I've actually seen in some of the exhibitions really your miniature spectrometers. So if we speak about customization, you know, now we're trying to convince Dan to substitute his little prism. So then, what will be your requirements for this diffraction element to work in your system?
So for me, definitely wavelength range. So at the moment we are vis-near, so I think you're probably covering that, but we're going down, let's say 380 to 1000 nanometers as our range. So hopefully you've got something that covers that, Thomas.
Absolutely, that's pretty standard, I would say. Yeah,
and it will be tiny then.
Sorry?
And it will be tiny. It will be really the size of my fingernail.
Exactly. I mean, I didn't mention that, but we make all our gratings on a wafer-based technology. So they're based on fused silica wafers. So the smaller the grating, the more you can have on one wafer. So of course that also helps drive down cost.
Thank you so much, Thomas. Dan, are you convinced?
I'm almost convinced. I'm definitely interested, Thomas. We'll have to catch up.
That's great. Let's talk.
Okay. Perfect.
Yeah.
And since we've moved to spectrometers, I would actually like to invite to the floor our last speaker. It's Tech5 USA. And Arindom Saha, that are actually the providers of entire spectroscopical systems used in industry in inline for the characterization of the technological processes. Arindom, tell us what's on your mind, what's new with Tech5 USA, and how you can help your industry partners sensing gas and liquids.
Hello, everybody. So my name is Ari, and I work for Tech5 US as a business development manager and also as an application scientist. So today I'm going to talk about process-on spectroscopy for monitoring refinery applications. So first, to give you a view of the market and technology sectors we work in, we support. We do have supporting in the thin film industry, chemistry, petrochemistry, environmental and mining, pharmaceuticals, biotechnology, food, feed and beverages, agricultures, agrochemicals. We also do OEM system integrations, and we also distribute our product lines and our sister company product lines under the LioniX group in the United States. The first application I'm going to talk about is gasoline blending, which is very common in the refinery and the petrochemical sector. I apologize for the slides jumping. How we can do that? It's a very interesting way a non-invasive way, easier way to determine physical parameters like RON, MON, and RVP, which is read vapor pressure. Typically, the industry uses a knock machine to do that, which is time-consuming, makes a lot of noise, has a lot of pollution side effects and stuff. Here, just by using a non-invasive Raman spectroscopy in the wavelength range from 500 to 3100 wave numbers, we can actually see the corresponding peaks of all the components in gasoline at their characteristic frequency shifts. And then if we get the time-stamped primary data from the customer, we can build a chemometric model. And from that, we can determine the research octane number, motor octane number, read vapor pressure, and a bunch of other physical parameters which are required to qualify the quality of a fuel before it goes for commercialization. And this way, what it does is that it produces the fuel with the right octane number, and you don't have any giveaway, and in the process, you don't have to incur any financial loss. The next, I'm going to talk about that was a liquid monitoring. This is about gaseous monitoring. We are able to monitor hydrogen at various pressures using our process Raman spectroscopy and our Raman gas probe. We did some tests here at various pressures of hydrogen, 7 different pressures actually, from 15 psi to 105 psi. And you can see that using our system, we were able to see even the ortho and the para-hydrogen rotational transitions. All right. So we are able to tell you the ratio of ortho and para in your metrics, as well as your hydrogen composition in your process metrics. Hydrogen is ubiquitous in the petrochemical world, and we get requests for monitoring hydrogen all the time. And here we can clearly show you that we are able to do it with our process Raman spectroscopy and Raman gas probe. This is a picture I have here from a site installation at a customer. Yeah, so it was a site installation and how our site looks like. And finally, what can others do for us in Tech5 USA? If you are a capital equipment manufacturer in the food, polymer, meat processing, refinery, or chemical industries, Tech5 USA is seeking collaboration opportunities to integrate our online sensors for feasibility studies at client sites. And if that provides fruitful, then we can OEM with you to sell this equipment, sell these sensors. Also, are you interested in real-time hydrogen or other gas monitoring using non-invasive techniques? At Tech5 USA, we offer reliable solutions tailored to your needs. And more broadly, if you are exploring real-time, non-invasive optical monitoring of any process metrics, or know someone who is, we would be happy to discuss how our online spectroscopy capabilities can support your goals.
Thank you so much. Thank you so much, Arindom. You know, as the very large, really system integrator and system provider that works as the OEM with your final customers, you can really see well most of the upcoming challenges. So now if you're looking on the horizon, what do you think will be the next interesting trends?
So I think that slowly, as I talk and interact with my peers and colleagues from the industry, this online sensing is going more automated because there is a huge turnaround for skilled workers from industry to industry. So everybody's pushing on automation. That's where this online monitoring technology, which provides like a sensor actuator kind of closed-looped seamless control, it comes into play. So this is going to get more and more popular as time goes in, because we are seeing loss in skilled workers in the industry as we move in. So this is a big.
And because there was this question with the ecological monitoring maybe becoming not that important on the daily basis, but these sensing methods were always promoted for the oil and chemical industries. Do you see the shifts and tendencies there, more interest from something, or agriculture?
There is interest from every sector, but there are also rival competing techniques present in the industry, as are other competitors. So there is a need for online monitoring techniques, but it depends on the application and the nature of the spectroscopy. So we see it in different industries. We see it in semiconductors, food, petrochemistry, chemicals, everywhere. but it is very application dependent on what technology is going to be used.
Thank you, Arindom. I'm very sure there will be quite a few contacts to get in touch with you. Meanwhile, I noticed that many speakers, were always mentioning that one of the challenges or maybe one of the trends is miniaturization, how to make things integrated, how to make things smaller. And with this, I would like to ask actually our last speaker of the day, LioniX International, Erik Schreuder, how you can help to make things smaller, integrated, more robust, and potentially also cheaper for the large-scale field deployment.
So my name is Erik Schreuder. I'm from LioniX International, and we are a foundry making integrated photonic chips and also MEMS for. So basically, we make integrated photonic chips and MEMS chips for a broad range of applications, and of course, sensing is also one of them. And one of the main things is there that we, in our platform, we can basically etch features which enable basically to have a waveguide which can access a liquid, but it could also be a gas, and it can also be a different kind of sensing principle. Typically, you can measure, let's say, in absolute field, you can phase delay and measure refractive indexes of the solution. If you have a transducer material, for example, you can also detect certain gases. It's also used for a lot of biosensing applications. But besides just refractive index sensing, you can also have large spirals in there where you can measure, based on the evanescent field, all kind of absorption processes for the silicon nitride platform that typically is within the range of 400 till 2300 to 2.2 micron. So really in the more lower end of the infrared and the visible region where you can measure with. And this can all be combined with all kinds of techniques like integration of photodiodes, integration of laser diodes, but also building the complete system around it. For example, you could have, let's say, a laser with an internal reference based on a gas cell, which is integrated on the chip itself. Also, spectroscopy methods are possible, which are typically used for OCT. So you can have AVGs and have a full spectrum measured in the visible region. So there's really a broad range of applications possible, all with silicon nitride in terms of sensing, and this also makes miniaturization. It can make it very, very compact. So you can have everything all in one, in the sense of the sensing element, but also the lasers and the detection stuff, but also all the structures for spectral separation of your optical signals. Here in the bottom left, we also have let's say this a dedicated system where it's basically combined with a fluidic flow cell, where we can just flow particles through a optical path, where we can detect under different angles, basically scatter of particles. Also part of fluidic sensing there. So there's a broad range of applications possible. So it really depends on what the customer wants. So what we see is applications in Raman, in absorption sensing, in evanescent field sensing, a lot of biological biosensing stuff where you have basically all kind of the elements on the surface which can react and increase basically the mass and change of index locally of the refractive index sensor. So are there specific questions related to this?
I have one question. What wavelength range can you cover?
Typically the range is from 400 nanometer till 2.3 micron. So that's basically the visible range of the silicon nitride. Beyond that,
of course, you can integrate active material on it, and you can make very narrow line with constantly tunable laser over that range.
Yeah. So there's basically silicon nitride itself is passive, but we can add a lot of components. So hybridly integrating. So we can make pockets, for example, to put gain sections in there. So we basically can make a laser with let's say the gain section is the active material, and then you have the triplex is, let's say, the advanced mirroring, let's say it this way, and then you can make very narrow bandwidth lasers for that, which is also typically used for gas sensing. Quite interesting, very narrow bandwidth and tunable over 100 nanometer range. So there's a lot of possibilities.
Congratulations, Erik, on everything that you are achieving with LioniX, the entire LioniX team, and also congratulations to all the speakers today. Today was a really interesting topic. It was gas sensing, and we needed to match the system integrators' demands with the technology of our members. I was particularly excited to see how the fibers of Art Photonics or the lasers from mirSense could actually be integrated in the future on systems as NIST or Aerodyne. Let's continue working together. If you want to continue supporting what we do at Optica, please join as a corporate member. And with this, thank you for another great online industry meeting.